yourself rather than just listening. And so let me share my screen and we can get started. Can you see this?
Yes. Yes.
Okay. Now I can't actually see the chat window while I'm presenting. So if you want to ask a question or answer a question or anything, please somebody can just speak out loud so that I can come over and answer that. So today we're going to talk about math and galaxies and how math is connected to galaxies. So I like to start off right off the bat with a little activity for you to do. So here's a challenge. And I'm going to give you some sequences of numbers. You can get out your paper and pencil. And what you're going to do is try to find the next 3 terms in each sequence. There's going to be a bunch of them that I'll show you in just a minute. Each one is harder than the last. And you can use a calculator if you want, but if you want an extra challenge, do it by hand. And I just want to make a note that I know there are a variety of different students of different ages and different grade levels in the session today. So basically, each challenge that I give you will have several different degrees of difficulty for different students of different levels. And you can try whichever one you think is right for you. Now, if you finish all of these challenges, you can try inventing your own sequence that is sort of the same type of sequence, but is maybe different in some way. You can add your own twist. And I encourage you to be creative. So here they are. Here are patterns of numbers, and what you have to try to do is find the next 3 numbers in the sequence, and I'll give you 5 minutes to try that out. Feel free to ask questions as we go along. You can type into the chat.
Can you show the sequences again?
You can't see them? Oh, I see. Yes. Yes, I see. I understand the problem.
If you want to stop sharing and start sharing it, okay, good. That works.
I think I will actually stop sharing and start sharing again. The problem is I'm on 2 different Google accounts right now. So let me just fix that. There we are. I think that should be better. Okay, now I can see all of you and also share my screen. So I hope that's working okay. Now I can see one student has already typed their answer to the first one in the chat and the second one. So if you don't want it spoiled, don't look in the chat. But great job to those of you who have already put your answers in the chat. I think some of you are already noticing that once you get to the third one, it's getting a little bit harder.
I'm on the third one.
That's great. Good job. I think a few people are on the third one. Ooh, somebody's on the fifth. Very nice. Just going to give you 1 or 2 more minutes to try these out. I know it's not maybe enough time to do all of them, but you can try them again later on your own time if you're curious. I'll give you one hint for the third one, if that's what you're on, and then 1 more minute, and then we'll take up the answers. So the hint for the third one is that you have to think about multiplying by 2. Anton, nice job. Well done. That last one is quite tough, but I believe in you. Oh, that was fast on number 6. So now you can invent your own, Anton. Try to fool all of us. Brian, it looks like you figured out the third one. Good job. Okay, so I'd like to take up these challenges. Now I'm curious if anybody would like to explain how they figured out the first one. Maybe one of the younger students would like to explain how they figured out the first one. Feel free to turn on your, yeah, Toby raised his hand. So Toby, you can go ahead.
So for the first one, it is the sum of the two numbers before it. So 1 plus 1 equals 2. 1 plus 2 equals 3. 2 plus 3 equals 5, and so on. So 5 plus 8 equals 13. And then 8 plus 13 equals 21. And 13 plus 21 equals 34.
Fantastic, Toby. You got it absolutely perfect. Great job. Would somebody else like to explain how they figured out number 2? Burton, why don't you go ahead?
Okay, so I found the sequence is, so it's +2, +2, +4, +6, +10. So you add the difference between the previous two numbers. So that's the difference between the next number. So then the difference is 6 and 10. So add it together, it's 16. So 26 plus 16 is 42.
Very
And so
nice.
it's just 10 and 16. So then it's 26. So 42 plus 26 is 68. And
Awesome.
16 plus 26 is 42. And 68 plus 42 is 110.
Awesome job. Great job, Burton. I'm going to skip ahead. Why don't we look at number 5? Does anyone, one of the older students, want to explain how they figured out number 5? If they were able to figure out number 5? I can see that a couple of the older students in the chat think they have an answer for that. Let's see. I see AL, somebody with the Anton, I think that is, would like to explain.
For number 5, the pattern was basically the sum of the last 3 numbers. But the sum of the value of a term is the sum of the 3 previous terms.
Right, so that one is just a little twist on the first one. So instead of adding the 2 previous terms, you add the 3 previous terms. Okay, so I'm going to show you all of the answers now because we are going to move on to the next part of the lesson, even though we didn't take up all of them, but I'll show you all the answers in just a minute. But first, I want to tell you about the Fibonacci sequence. So this guy is Leonardo Fibonacci. He was born in around the year 1175, which is almost 1,000 years ago, in a place called Pisa, Italy, which is the same place that you might have heard of, the Leaning Tower of Pisa. And also, construction on the Leaning Tower of Pisa started in 1173, which is very close to the time that Leonardo Fibonacci was born. So that's kind of an interesting coincidence, don't you think? Here's a couple pictures of the Leaning Tower of Pisa if you haven't seen it before. And people like to take funny pictures around the Leaning Tower of Pisa. These ones are a couple of good ones. Now, this first sequence that you probably have seen before is the Fibonacci sequence, the famous Fibonacci sequence. And you just have to add the previous 2 terms as was explained by one of your classmates. Now, the second one is also a Fibonacci sequence. And I think it was Burton who explained how he got the answer. But actually, another way you could do this one is the same way as the first one. You just add the 2 previous terms in order to get the next term. Well, you may notice that's exactly the same method as the first sequence. The only difference is the 2 starting numbers are different. And so this is also called a Fibonacci sequence, just not the most famous one, because the most famous one is the one that starts with 0 and 1. The third sequence is also a famous sequence, which has its own name, and that is called the Pell sequence. The way this one works is you add the second last term to 2 times the last term. So for example, you do 0 plus 2 times 1, and that's 2. And then you do 1 plus 2 times 2, and that's 5. And 2 plus 2 times 5, and that's 12, and so on. The fourth one is very similar to the third one, except instead of multiplying by 2, you multiply by 3. So 0 plus 1 times 3, 1 plus 3 times 3, and so on. The fifth one was already described by Anton, and that's to add the 3 previous terms. And the sixth one, this is the hardest one, so you add 2 times the second last term and 3 times the last term, the previous term. So you would do 2 times 0 plus 3 times 1, and that gives 3. And then 2 times 1 plus 3 times 3, and that gives 11, and so on. And let's see if anybody got the right answer for the last one. Did anybody get 495, 1763, and 6279? I'm not sure I saw it. I see Anton has his hand up. Well done. Now, I think you can all agree that now that you've seen the pattern for each of these sequences, they're all basically the same type of sequence, just with little variations and little twists. And that's a very interesting thing to do in math, is when you find a pattern, you find different variations on the pattern, and then you can learn even more about those types of patterns by looking at different variations. So let's move on. Oh, and also, if anybody finished, I had an extra challenge, which was to invent your own sequence. Now, if anybody did that, please write it in the chat, because I think that would be an interesting challenge for your classmates. You can give it a name. You can say, this is my own favorite sequence, and Brian's sequence or Burton's sequence or whoever invented it, and you can put it in the chat and see if your classmates want to try it a bit later on. I also want to show you that if you invent your own sequence and nobody has ever invented it before, and if it's a useful and significant sequence, that you might actually be able to get it published online in something called the Online Encyclopedia of Integer Sequences. Now I'm going to go there. I'm just going to bring that over into my shared tab, and I'm going to show you the Online Encyclopedia of Integer Sequences. And if we type in 0, 1, 1, 2, 3, 5, 8, 13 and search, and it's going to show us all of the sequences that start that way. Now, there are actually 78 different sequences that start that way, but it usually sorts it by the most famous. And so you can see here, the very first result that we get is the Fibonacci numbers. and you can see a whole bunch of them, and you can see some other comments about them and so on. And this probably looks pretty complicated. There's a lot of advanced stuff going on in here, but this is sort of like the Wikipedia, but just for number sequences. And actually, there's a little history to this website, which is that it was started, I think, like 50 years ago. But obviously, at that point, oh, actually, even more than that, you can see right here, it was founded in 1964, and at that point, it was not online. It was just kept in a notebook by this professor named Neil Sloan, who is still a math professor today. And there's lots of YouTube videos where he explains some of his favorite number sequences that are really great videos that I encourage you to go watch. And so I thought that was kind of cool, and I would show that to you. Now I'm going to go back to the presentation and just do a quick little check on the chat to see if there are any questions or anything. I can see a couple of people have written their own sequences in the chat. And so students are welcome to try finding those patterns later on when you have some spare time. Now, just to formalize our definition of the Fibonacci sequence, this is a pattern of numbers. Every sum is the sum of the two terms before it. But I just want to point out that in order to fully formally define this sequence, I have to tell you the first two numbers. Because if I don't tell you the first two numbers, then you have no way of generating the third number and the fourth number and so on. So here, what we have is a formal definition of the Fibonacci sequence. If we say that f0 is 0 and f1 is 1, then fn is f of n minus 1, which is the previous term, plus f of n minus 2, which is the second previous term, so two terms ago. This is some algebra. Some of you might have seen algebra before, some of you may not have, but this is a way of defining something in math in a general way where you don't need to specify specific terms in the sequence. Okay, I'm going to move on now. Now I would like to talk about something called the golden ratio.
We have one question, Mr. Rutt. It's from Breton.
Okay.
So
Burton,
for the
go
one,
ahead.
Burton.
like we don't need to specify the term, but I think we need to specify like the n, because if the n is like 1 or you can't minus 2 or minus 1.
You're talking about here where it says n minus 1 and n minus 2?
Yeah.
Right. And so this formula specifies that in order to get the n term, you have to add the n minus 1 term, which is the term before, and the n minus 2 term, which is two terms before. So what you see inside this box specifies everything that we need to know. It specifies the first term. Actually, it's kind of weird, but in the Fibonacci sequence, this is called the 0th term, and then the first term, and then the general formula to get all of the other terms, which uses algebra to say the nth term is the n minus 1 term plus the n minus 2 term. So thank you for bringing that up and allowing me to clarify that, Burton. Okay. And now I would like to talk about something called the golden ratio. Some of you may have heard of this before. This is a very special number. It is usually represented by a Greek letter, which is called phi. And that's sort of like the Greek version of f, from what I understand. It looks like this. These are the symbols for the capital and lowercase phi in the Greek alphabet. You can try writing your own if you want. I think it's kind of fun to try drawing Greek letters because they have interesting shapes and it's fun to just try it out. And what is the actual number? Well, it is about 1.6. To be more specific, it's about 1.6180339887 and so on. Now, this is an irrational number, which means it is a decimal number, and the decimals go on forever, and there's never a repeating pattern. This is like pi. You might have heard about pi before. That's the most famous irrational number. You might have heard also about the square root of 2, which is another famous irrational number. And this is probably one of the top 5 most famous irrational numbers, is the golden ratio represented by phi. Okay, so what does this have to do with the Fibonacci sequence? Actually, we'll get to that in a second, but first I want to show you, how can you get this number? Like, where does it come from? How do we know exactly what all of these different digits are? Here's one way of calculating the golden ratio. Now, this probably looks pretty confusing because it's moving and it's animated. But some of you may recognize this type of mathematical calculation. It's called a continued fraction. And in spirit of math, you do study continued fractions. Now, in spirit of math, at least when I taught spirit of math, I taught mostly grade 5 and 6. And I know that I think it's in grade 6, you do continued fractions, but they don't go on forever. They stop at some point, right? So that you can calculate the answer. In this case, if we want to get the exact value for the golden ratio, we need to keep going forever. This is an infinite continued fraction, which is kind of weird. And you might be wondering, how can you possibly calculate a calculation that goes on forever? So this is a continued fraction, which you may have learned about in spirit of math. And as I was saying, this is one that goes on forever. And actually, it turns out when you get to higher levels of math, continued fractions are most useful when they go on forever instead of stopping at some point. But how can you calculate the answer if it goes on forever? So what we're going to do is we're going to find an approximate answer by starting with a simple version of the fraction. And then we're going to move up the levels. And every time we move up a level, we're going to get closer to the real answer. So this is your next example for you to try. We'll spend another 5 minutes on this. And so once again, if you finish level 3, you can try level 4, but in that case, you're going to have to, first of all, figure out the question yourself and then calculate the answer. And I also want to note that for these answers, you are going to need to use decimals or fractions to get the right answers. So here's level 1, and that is the simplest version of this continued fraction. Level 2 adds one more level. Level 3 adds another level. And then level 4, if you get that far, you can try to write it out yourself and then calculate. And then you can keep going to level 5 if you get that far. So try calculating the answers to these questions as a decimal or fraction. We'll spend about 5 minutes on this. Anton, I don't quite know how you're able to do that so quickly, except maybe you found some kind of pattern. So maybe what you can do is write out a general rule for the pattern. Let's call it level n. Can you write out an algebraic answer for level n of this continued fraction?
I got 1.4.
1.4.
3 levels, I think.
So I think Toby wrote the answer for the first one is 1.5. So 1.4 is close. Maybe try it on your calculator just to make sure you're doing the decimal operations correctly. Very good, Anton. So Anton, your next challenge is, can you figure out the actual value of phi? Not using a decimal, so in a non-decimal representation. Is there some way that you can use your rule to actually get the value of phi?
It is 1 and 3/5. So it is 1.
Oh,
it
are
is
you
1.
on, which level are you on, Burton?
3 levels.
You're on level 3?
Yes.
Yeah, 1 and 3/5
So
is cool. Yeah.
I'm just So I'm just writing a few number of levels and I'm starting from bottom to the top.
Yep.
That's like the easiest way to do it.
Yeah, that's the right way to do it. On a continued fraction is you start from the bottom and then go to the top.
Yeah. Because at the bottom there's a pretty solvable thing.
That's right. Yeah, that's the only place that you can find something that's actually that you can calculate, and then you have to go from there. Anton, nice. So how did you figure it out? Agreem, that's right. Yeah. Now, Agreem, I'm not sure if I'm saying your name exactly correctly, but do you know the relationship between the two different sort of versions of the golden ratio? Yeah, well, they're both solutions to the equation that give the golden ratio. And so technically you can say there are two of them. And I guess, in a moment, we're going to look at some other ways of calculating the golden ratio. And I think that the more common version of it works for some of the methods, and then the less common doesn't always work. Okay, lots of great answers happening here. I'm going to show the answers for these challenges, and several students have moved beyond these levels and started doing some more advanced things, and I think that's wonderful. So level 1, here are the steps, and you get 1.5 or 3 over 2. Level 2, you get 1.67, or you can write it as 1.6 repeating, or you can write it as 5 over 3. Level 3, you get 8 over 5, or 1 3/5, also known as 1.6. And I just want to point out, you may notice that at each level, the answer does get closer to the golden ratio. And so by the time we get to level 3, we're quite close. We're within a tenth of the actual value of the golden ratio. Now, we're not going to get to the point today where we can actually solve an infinite continued fraction, because that takes some more advanced higher levels of math, but it is possible to solve an infinite continued fraction. And that is a very interesting field of math. I hope you get there someday. Some of you might have already seen that before. Now, I'm going to show you some other ways to calculate the golden ratio. This is, to me, one of the most interesting things about this number is that there are so many different ways to calculate it, because it pops up in all these different places that seem to be like not related to each other, which I think is really cool. So I'm going to show you 4 different ways to calculate the golden ratio. And I'd like you to try at least one of them. And if you figure it out, you can try another one. Some of them are harder, some of them are easier. And here they are. So one way is similar to what we just did, except instead of a continued fraction, it's a continued square root. The second way is was actually pointed out by a couple of students already, but you can divide each term in the Fibonacci sequence by the term before it, and you write down your answer as a decimal and keep moving along the sequence. The third way is to solve an algebraic equation, and this is the equation right here. If you solve it, then you can get the golden ratio, and also a second answer, which we were talking about there with a couple of students. And here's a fourth really interesting way. I'm curious to see if anybody wants to try this. If you draw a regular 5-pointed star, and you look at these different colored line segments, if you find the ratio of the red to the green, it is equal to the ratio of the green to the blue, and it's also equal to the ratio of the blue to the pink, and all of those ratios are equal to phi. So can you actually construct geometrically the star shape and solve for the golden ratio using your diagram? So try one of these 4. I would say probably the easiest one is the Fibonacci sequence, the pink one. And then the second easiest is the continued square root. And then I'm not really sure which one is the hardest of the 2 bottom ones. So try one of those, and we'll spend a couple minutes on this. Andy, that's a very interesting strategy. I think that's great. And anybody who's interested in algebra and figuring out the algebraic equation, you might want to look at what Andy wrote in the chat about the square root method. You can use that as a hint to try to do it yourself. Oh, I just noticed that Isaac, you have your hand up. Would you like to ask a question?
I found x in the algebraic equation for like the square to the quadratic equation, but like how do I use it?
You found x. So what is the value of x? What did you find?
I found x. Wait, I found 1 plus minus square root 5 over over 2.
That's good. So what you can do is test it out on your calculator. So first of all, you have two answers there. One of them is the one that uses the plus, and then the other one uses the minus. So you can have that as two different answers. And then you can try punching that into your calculator and see what the decimal value of that is. And then I think you should see that one of those two answers is the number that I showed you before on the previous slide. So basically what you have the answer already. So you asked how to use it. Well, there's no more using it. You've already found it.
Yeah.
Did anybody else notice anything that they want to share with their classmates about using any of these methods to find the golden ratio? Agrim, I just want to go back to what you wrote before. You asked if the second one has any significance. So if we look at the star, the 5-pointed star, I think you can see that the ratio of a red side to the green side, for example, that can't be a negative number because we're using positive side lengths. So in a geometry problem, it wouldn't really make sense to have a negative ratio. And so that's why the second solution to that equation is less well known, because it doesn't always make sense depending on how you've figured out the golden ratio. So I think that might be one answer to your question. Okay, I'd like to move on, everybody. I know once again that wasn't a whole ton of time, but feel free to try these some more on your own time a bit later on. And I'm just going to read what Agrim wrote. For the star one, if you create similar triangles between the lines and manipulate the ratios a little bit, you will get a quadratic equation describing the ratio of the two colored sides. Yes, that's correct. And I'm just curious, Agrim, is that quadratic equation by any chance this one down here on the bottom left corner? And so it turns out that lots of these different methods, when you figure out some sort of strategy for doing them, they eventually reduce to this equation in the bottom left. And for any students who know how to solve an equation like this, of course, you're going to get the same answer if you end up with the same equation using different methods. And so you can see that at a deep level, the different methods are related to each other because a lot of them lead to the same equation, which then, of course, leads to the same answer. And so we can find the connections between different fields of math in the algebra. Okay, so let's move on now. And I just want to remind you that we started off with the slide that says math and galaxies. So wait, what does this have to do with galaxies? Well, let's talk about something called a golden spiral. And this is where you're going to need your square paper. I asked you to bring square paper specifically. So here's, I think, pardon me?
Sorry, Mr. Rutt, I think Burton raising a hand. Burton, do you have a question?
Yeah, question, yeah.
I think he is good now.
I don't see a question.
Mhm.
Okay, so this is the last activity for today. Then I'm going to show you a few things and then we are going to be done. Now, here's the activity. Using your square paper, these are the instructions. You're going to draw a square with side length 1. Inside that square, you're going to draw an arc of a quarter circle from one vertex to the opposite vertex. And I've drawn an example down here so you can see exactly what I mean by that. Then you're going to repeat steps 1 and 2 with another square of side length 1, such that the previous arc continues into the current arc. So basically the arc keeps going without jumping over to some other part of the page. And then you're going to you're just going to keep repeating those steps, except the size of the square is going to increase. So you're going to do size 2, then size 3, then size 5, and so on. And you're going to only use Fibonacci numbers. And you're going to keep going until the next square doesn't fit on your page anymore, and see how far you can get. So let's just spend a couple minutes on this. I hope those instructions are clear. If you're not sure, you can hold up your page and I can see if you're doing it the right way. And you don't actually have to draw the squares if you don't want, because you have square paper, so you can just draw within the squares if you prefer. I'm going to draw my own here. It can be hard to draw a quarter circle arc perfectly. You can use a compass if you'd like, but it's hard to do it freehand, isn't it?
I got a curl sort of thing.
Exactly, yeah. I like that way of describing it, a curl. That's exactly what it looks like, isn't it? Shashwath says they got a snail shell. Yeah, I think it also looks like a snail shell. That's absolutely right. Like a rounded G. Yeah, I agree. These are all really good ways of describing the shape, and I think you're all on the right track, at least from those of you I've heard from. Try to think of some other shapes that it reminds you of, because we're going to talk about that in just a minute. Okay, so I'm going to show you what it's supposed to look like. And if you think it's fun to draw this shape, I personally do think it's fun. It's like a fun doodle to do on your page. You can try to make it as big as possible when you have a bit more free time. So this is what it's supposed to look like. So you can see the size of each square is the important part. So the first one is 1 by 1, and then another 1 by 1, and then 2 by 2, 3 by 3, 5 by 5, 8, 13, and then this one goes up to 21. Was anybody able to? Pardon me?
I also got the 21.
Very nice. That's pretty big. That's pretty hard to fit on a page. Sometimes I find I try to get to 21, but I started in the wrong spot, and so I ran out of space. So that's great that you did it that way. Shashwath, you did it reverse. That's totally fine. So it's sort of like a backwards version, but it's the same shape, right? Just backwards. Awesome. Here's just another picture showing the numbers. And you can see that these are the Fibonacci numbers. Now this is called a golden spiral, and we created it using math, using just numbers and drawing and geometry. But it turns out, and some of you have already noticed this by describing the shape, that golden spirals show up in nature too. And I'm going to show you some examples of that. Here's some extra reading for your interest. You can read this a bit later on if you're interested. So we've heard of the golden ratio today, but there's also the silver ratio, the bronze ratio, the aluminum ratio, and many more. And if you're interested in this type of math, then I think you should read this article. It's pretty interesting. It's not that long. So here are some examples of golden spirals in nature. This is a plant called the spiral aloe, and you can see that it is a very similar shape to what we just drew. Somebody already mentioned a snail shell, and there you go. So if you match up your shape with this spiral, you're going to find that it's pretty close to the specific type of spiral that we drew. Weather systems, if you look at certain kinds of storms, you will see that they form into spiral shapes. And finally, drum roll, galaxies. Now, our galaxy is a spiral galaxy. And there are a couple different kinds of galaxies, but spiral is one of the most common ones. And you can see that, once again, the spiral shape of the galaxy is pretty similar to the spiral that we drew. Now, if you're wondering, is it exactly a golden spiral or is it not exactly that specific shape of spiral? There are ways of actually calculating how close a specific spiral is to a golden spiral. And you can say, you can determine whether it's, 50% related, or maybe it's more like 99% related. There are ways of doing that that I'm not going to get into today, but I just wanted to mention that. And I'm just checking the chat. Isaac says, looks like some galaxies. I assume you wrote that before I showed you the picture of the galaxy, Isaac. So that's a very good observation. So now the last part of today's session is I would like to show you a little bit of music. And specifically, this is a song that I wrote, which is inspired by the Fibonacci sequence. Now, who here takes music lessons or knows a little bit of music? So you don't need to know very much music to understand the Fibonacci pattern in this song, but I'm just going to show you one little thing. And that is, if you look on a keyboard, then you can number the notes. And now when you learn music, you probably learn the letters C, D, E, F, G, A, B, and so on. And you probably don't normally use numbers, but it actually turns out that numbers are very common in music, especially when you play certain types of music. So for example, when you play rock music or pop music or jazz music, musicians use numbers a lot to describe the chords they're playing and the notes they're playing. It's a little bit less common in classical music and in music lessons, but it is actually a common thing to do. And so in this particular case, we are playing in the key of C major. And that's why C is 1 and D is 2 and so on. Now, if I wanted to play a song in a different key, like let's say I wanted to play an F major, then F would be 1, G would be 2, and so on. But we're playing in C major, so this is how the numbers go. Okay? So in a moment, I'm going to show you my musical composition, and it uses the Fibonacci sequence. Now, you might remember that the Fibonacci sequence actually starts with 0, not with 1. And so what I did is I said, well, if C is 1, then we're going to go down 1 note to the previous B, and that's going to be 0. And then C is 1, and then we have 2, 3, 5, and then 8 is not shown here, but that would be the next C, would be 8. And so you're going to see the Fibonacci sequence in this song. Now, I'm going to stop sharing my screen because I'm going to share the program where I make the music. And so you can see that. Hopefully, you'll be able to see that okay.
Is it a piano score?
No, it's not a piano score. This is actually something called a digital audio workstation, which is how musicians make music on the computers. And I'll show you all the little pieces of it. And you can do this at home. There are free beginner versions of this type of software. If you use a Mac, you can use something called GarageBand. And if you use a Windows, I don't actually know the best one for Windows, but there are others out there that you can use. So I'm going to share my entire screen so that you can see this software. And here it is. Can you see this?
Yes,
Yep,
we can.
I'm seeing nods. Okay, perfect. And can you hear that?
Yes.
Excellent. Okay, so here's the song. Now you can see that there are 5 different pieces, but actually if I open them up, there are more than that. So up here we have the melodies, the bass, the chords, the sound effects, and the percussion. So I'm going to start with the melody because that's where the Fibonacci sequence is. So let me open it up like this, and you can see if I go over to where the melodies start, we have 1 note, and then later on we have 2 notes. And I'll just look on the keyboard, and if you know music, you might know this is a B and this is a C, and so this is our 0, and so the melody is playing 0, and then it's playing 0, 1, and I'm going to play it, and then I'm going to tell you as we go along. 0, 0. I'll try to sing it too. 0, 1. 0, 1, 1. 0, 1, 1, 2. 0, 1, 1, 2, 3. 0, 1, 1, 2, 3, 5. 0, 1, 1, 2, 3, 5, 8. And that's the melody of the song. Now I'm going to play you the other instruments as well in just a second, but let me just point out this sound that you're hearing. What is it? Well, it's not a piano, obviously. It sounds kind of spacey, like it comes from outer space. So that was what I was going for because this song is about galaxies, right? So I was trying to find a sound that sounded like it was coming from outer space. So now let's play it along with the bass. So actually the first instrument you hear in this song is the bass. And this sound also sounds like something that came from outer space. So it goes like this. Now the melody is about to come in. And here we're going to get some chords. I'm just going to play that by itself. So as the song develops, it adds more instruments and it becomes a fuller song. So let me just play the chords for you. They sound like this. And then later on, we also add some percussion. So you can hear the drums happening now. And then it's going to repeat the melody again with all the instruments there. You probably also hear some sort of spacey sound effects, and that's, I think, in this track here, the sound effects. So let me just play what these are like. So I'm going to solo that. So there's a sound effect that sort of makes it sound spacey. And here's another one coming in that adds a little bit of color. So I was just looking around for sound effects that made it sound even more like it was coming from outer space. And then I'll just point out a couple more things. So in the melodies, I already played the melody for you, but you'll notice that we do the melody once, and then we repeat the melody, but the second time there's a copy of it, and it's up an octave. So now it's, you hear more of the melody and you hear it higher up. So let me just play that for you as well. You can hear, this is the higher one by itself. Oh, no, it's not. Sorry, 1 second. Here you go. There's the higher one by itself. Now with the lower one. And then the third time the melody comes in, there's a third copy of it, and it sounds like this. I'll put that together with the other 2 melodies. and so on. Anton says it sounds like music from a science fiction movie. I'm really glad to hear that because that's basically what I was trying to make. So thank you, Anton. Lucy says it's synthy. Yes, lots of synths. Pretty much everything in here is a synth other than the sound effects and the drums. Does anyone have, so what I'm gonna do is I'm gonna play a short video for you and you're gonna hear the full song. But before I do that, I just wanted to ask if anybody has any questions about the musical composition or anything about the song. Please feel free to ask now before I show you this, this last little bit of the presentation. Thank you, Burton. Thank you very much for the compliment. And in a moment, you're going to get to hear the full thing. Shashwath asks, how can you make it? I will show you a very brief demonstration on how to actually make it. So this is the software that I use. It's called Logic. You can see up here. This is a Mac program. It's basically like the professional version of GarageBand, but you can do everything that you see here. You can pretty much do it in GarageBand. Now, how to actually make it. So I can just show you that very briefly. You can do it all on the computer. You don't actually need to use an instrument, although some people like to use a real instrument and play it into their computer. So if I wanted to make a new part of the song, I'm going to put it over here. And then if I want to put some notes in there, what I can actually do is just use this tool called the pencil tool. You can see my pencil right here. And I can actually just click and it makes a note. And then I can click and make another note. And if you want to, you can make music just by clicking into the box like this, clicking on the right notes that you want. And that is one way of making music on your computer. And that's pretty much what I did for this song because it's all synths. Like Lucy was saying, I didn't play any real instruments for this one. Sometimes I record a guitar or I record myself singing, but in this case, it was all done on the computer. And so what I just drew in here, I can draw a few more notes and we could hear what that sounds like. Oh, hang on a second. I'm not sure why that's not working. Actually, I think I know. No, I'm not sure why that isn't working. It's muted for some reason. It should be working. Oh, well, maybe if I'll just try one more thing. I'll just try dragging it over here and I'll see if that works. Yes. So Shashwath, that was the music that I just made just now, just by clicking, and that's how you can do it. I'm going to get rid of that. Anton says they use Soundtrap for a school project. And so that's maybe a good piece of software that you can try if you're interested in that. Isaac says you have the same background on Mac as me. Nice, good one. Okay, so with that, I would like to show you a brief video. So I'm going to stop sharing and then I'm going to go to YouTube and share that tab. And share the audio as well. I don't know why I need to do this. Anyway, so this song is called Fibonacci's Fantasia. That is the name of the song. And what you're going to see is an explanation of how to make a golden spiral, which you've already done, so you know that already, but you're also going to hear the music in the background. And I hope you enjoy it. It's about 2 minutes long.
Meet Grammarly Go, your go-to solution for getting quality work done quickly.
And that's the end of the video. So with that, I'm going to stop sharing YouTube and just go back to the presentation. And I just want to recap what we did today. So today we learned how the Fibonacci sequence works, how to build and identify similar sequences, how to use the Fibonacci sequence to find the golden ratio, some other ways to find the golden ratio, how to use the Fibonacci sequence to draw a golden spiral, some examples of spirals in nature, and finally, how to use numbers to inspire music. So I hope you enjoyed the presentation. That's the end. I want to thank you very much for your time, and thank you to Spirit of Math for hosting this. And if there are any questions, I'm happy to stick around and answer them.
Yeah. Thank you, Dave, for the wonderful session. It was very interesting to note different ways to calculate the golden ratio and creating golden spirals using math. We also enjoyed the Fibonacci song.
Thank you so much.
On
Thank you for the
on
comments.
behalf,
Yeah, go ahead.
Yeah, on behalf of the Spirit of Math team, I would like to extend my gratitude once again. Thank you everyone for joining this session.
Thank you, and thank you
Have a great day.
Thank you for everybody for the comments in the chat. I'm reading all of them as you're sending them in. Shashwath, I think you might have a question. You have your hand up.
I like the music.
Thank you. And I can see that you have a drum kit right behind you.
Yeah.
All right, so you're a musician. That's great, and I hope that it's inspiring for you to start writing your own music.
There are some.
Burton, in answer to your question, Burton, yes, I composed that song. That's right.
Mr. Rutt, I have a question as well. How did you get the idea to come up with this?
With the song?
And the whole presentation?
That's a good question. Let me try to think. Well, I'm always trying in my teaching. I'm always trying to connect math to other things that are interesting. And so when I saw the golden spiral, I think I wanted to connect that to the Fibonacci sequence, and then obviously it's connected to galaxies. And so I decided to make a little video out of that. And when I was making the video, I thought, well, this video should have music. And so what music am I going to put into it? So it seemed natural to write a song based on the Fibonacci sequence. So I thought it all went together really well. Wonderful. And one more thing, could you maybe add those two links in the chat? There was the link on this sequence encyclopedia where students can put in their sequence. That would be great. And maybe you had a link for other ratios, the silver ratios. Do you mind putting this in the chat, please, as well? Yeah, I'll put those in the chat. I'm also happy to share the whole presentation if students want to look at it again. Okay, wonderful. Thank you so much. Are there any other questions? Well, thank you so much for joining, everyone. Have a great rest of your Sunday. Thank you so much, Mr. Rutt. We would love to have you with us again soon. That was really great. Thank you so much. I would love to. Thank you.
Yeah. Bye.
Bye.
Bye-bye.
Bye.
And I'll send the link for the video as well.
That would be great, yeah.
Okay, thank you so much. I'm going to go.
Thank
a
you.
great
Bye.
Thank you.
Bye.
Bye.
Thanks a lot. Bye.
All right, thank you.